Welcome to springlib.
Alrighty, so got a Coast Guard vessel that is hanging out here at the origin of our coordinate system. This is north, this is east, and this is actually a compass rose in our legitimate coordinate system. Our y-axis is actually right here. I'm pointing it this way. That's our y-axis. Find that as y, and our x-axis perpendicular right here. That's our x-axis. Not as important in this problem, but we have to have it defined so we can orient our axis system. Cool. So there's our y-axis. You can see this is a rotated Cartesian axis, and you can see I have a compass rose kind of thrown in here as well. Now the Coast Guard vessel is here, and it notices the ship 15 degrees with respect to the north direction here, and it notices this ship out here, roughly a distance of 26 kilometers. 26 kilometers away in this direction. Okay, so and it sees this ship moving at a certain distance, or a certain direction. The ship out here, or the boat out here rather, is moving at this direction here, 25 degrees, with respect to that original angle right here, 25 degrees. Okay, and it's essentially 40 degrees from our origin. If I were to move this vector down to here, this would be 40 degrees, but let's not overcomplicate things that much. So that's the picture so far, and this guy has a velocity vector as well. He's moving at 26 kilometers an hour. That's his speed. So let's go ahead and develop this velocity vector real quick for the ship. I'm going to call it V sub S. And we know it's moving 26 kilometers an hour. So 26, and we're going to say 26 sine 40 degrees for the I direction, or the X direction here. And you imagine if I drew this vector here, the 40 degrees is over here, so we're going to want to use sine. It's opposite. So use sine 40. And of course, we have to keep in mind that we are already a certain distance from the ship. We're not, the ship is, this boat is not at the origin. We're at the ship where the Coast Guard is. We have to include that 15 unit vector there as well. Plus, and now we're going to take care of the J component, and that's going to be the 26 again, which is the velocity of the boat, and it's cosine 40 degrees here this time. Take part of the other component, this one. All right. And of course, this time we also have to keep in mind that original position of our Coast Guard ship. So we have minus 15J there. And then if we clean these guys up on both, and then combine these guys, we get velocity of the ship. And we got a nice unit vector notation cleaned up as 10.99 in the I direction, plus 23.56 in the J direction. There's our unit vector. Cool. And then we're also going to make a velocity vector of the boat that is coming to get them. Just keep in mind, that's what we're trying to do here. We're here at the vessel in our Coast Guard ship. We see this boat flying past us here. Now we want to get that boat to chase this guy. So the Coast Guard little fast boat is going to depart from this at a certain direction. And that's exactly what we're trying to find, is that direction that he's going to leave at. This angle right here, essentially. So that's what we're working for. But anyway, so let's try to figure out a arbitrary velocity vector for the velocity of the boat here. It's called velocity of boat. We'll call that 50 sine theta. That's that theta that we're going to attempt to find here. Sine theta in the I direction. plus 50 cosine theta in the j direction. Because we know how fast we're going to be moving. We just got to figure out what angle we have to depart at. So that's that theta that we're looking for there. All right. So now what we're going to do is we're going to use our kinematic equation to analyze the motion. And we're going to do it first for this ship here that's moving this way. So we'll do it for that first. This one right here, the first velocity vector that we found. So we'll go find that using the x. We'll use this kinematic equation. X final for the ship is to be equal to x initial plus velocity in the x direction initial times t plus 1/2 acceleration times time squared. Conveniently, there is no acceleration. It's moving at a constant velocity. So this part will go to 0. And we can also set our initial part as 0. And you can find out your x final for the ship will be equal to this velocity times time, which we already know that velocity in the x direction initially is 10.99. 99 times t. Just this part right here. Cool. All right, now we're going to do the same thing now for the boat. So we can do that. I'll do it over here. X final for boat. And same argument that I just made. We can kind of skip a little bit of a step here. We're not going to have an acceleration vector, so don't worry about that. You're just going to have your velocity vector and time. But of course, this time it'll be for the boat. So we're going to have new x initial, and I suppose I should probably put a little b here so we know it's for the boat. Initial times time. All right. And if we go ahead, then we can plug in that we have this guy right here. It's at 50 sine theta. So we'll put that as 50 sine theta times t. Now we can actually set these guys equal to each other, right? Because we do want, at some point in time later on, you do want to have the same position vectors as this boat. This ship going this way, and the Coast Guard ship or Coast Guard boat that's attempting to chase them or catch up to them, at some point later in time are going to be the same tick mark on the x-axis, which I have to mention is actually here, the same tick mark on the x-axis. So we need to determine that so we can set these equal to each other. Let's do that right here. So we have x final for ship equals the x final for boat. And that's going to be the 10.99 t equals the 50 sine theta t. And very fortunately, you can actually remove time here. Dividing both sides by t, we actually lose these guys, which is nice. Then we can go ahead and solve for theta. We can divide both sides by 50. Lose those guys. And you have 10.99 divided by 50, which we take the inverse sign of that, the arc sign, just to clear that theta on the other side, which is going to be equal to theta. Now, that's how we clear that sign. All right. And that's equal to roughly 12.69 degrees. But that's not the answer yet. We're almost there. This is really close to the answer, what we just did here. But what we have to do, though, is we have to take that answer and we have to add 15 degrees to it, because we have to add this initial part to it, which is no big deal. We have to just add that to it. So we'll have 12.69 degrees plus 15 degrees, and we'll get our final answer of 27.69 degrees. So at that angle, the Coast Guard speedboat can leave and travel at its max velocity, which it uses, which is at 50 kilometers an hour. Head out that angle, and it can go and see what's going on with this boat that's traveling at this direction.